Have you ever wondered, where in space does time not exist? Or what type of environment is needed for time to be non-existent? Let's embark on a journey to unravel the enigma of time. Time, as we experience it on our blue planet, is a ceaseless flow. It's the tick-tock of the clock, the turning of days into nights, and the changing of seasons. We're all passengers on this river of time, moving from the past to the future. But here's the catch. Time isn't the same everywhere. It's not a universal constant, but a relative concept that bends, stretches, and even halts under the influence of speed and gravity. Albert Einstein, one of the greatest minds of the 20th century, shook the foundations of physics with his theory of relativity. He proposed that space and time are woven into a single continuum, a four-dimensional fabric called space-time. And this fabric is not rigid. It curves around massive objects, like stars and galaxies, creating what we perceive as gravity. Now imagine a spaceship zipping away at near light speeds. According to Einstein, time would tick slower on this spaceship compared to Earth. This is time dilation, a mind-bending consequence of relativity. So time as we know it is molded by the cosmos itself. Yet the question remains, where in this vast universe does time cease to exist? Could there be regions in space where the tick-tock of the cosmic clock comes to a standstill? What kind of environment would allow for such a phenomenon? The answers to these questions take us to the realms of black holes and the voids of space, where the rules of time as we understand them seem to break down. These are the regions where our understanding of time and its flow gets murky and mysterious. Now that we've set the stage, prepare to delve deeper into the mysteries of time and space. The journey ahead is filled with cosmic curiosities and paradoxes that will challenge our understanding of the universe and our place in it. So buckle up and get ready to warp through the fabric of space-time. Time, as we know it, is a man-made construct designed to measure the passing of events. But in space, the concept of time becomes a bit more complex. You see, the ticking of clocks isn't universal. It changes depending on where you are and how fast you're moving. This is the essence of Einstein's theory of relativity, a revolutionary concept that forever changed our understanding of time and space. Imagine you're on a spaceship zooming away from Earth at nearly the speed of light. Now, if you were to glance at your wristwatch, you'd see the seconds ticking away just as they always do. But if someone on Earth were to somehow peek at your watch, they'd see the seconds dragging by slowly. This is known as time dilation, a peculiar consequence of relativity. Time dilation can be a bit difficult to wrap our heads around because it's so far removed from our daily experiences. But it's not just theoretical. It's been tested and proven with precise experiments involving atomic clocks on airplanes and satellites. Gravity also influences the flow of time. It's a bit like a cosmic speed bump. The stronger the gravity, the slower time flows. This is known as gravitational time dilation. So if you were to stand on the surface of a massive star, your wristwatch would tick slower than it would in the emptiness of space. These concepts show us that time is not a fixed entity. It's flexible, bending and stretching in response to speed and gravity. This fluidity of time is a cornerstone of modern physics, a testament to Einstein's genius. Time, it turns out, is a slippery character. It's not as steady or as dependable as we might like to think. It's relative, contingent on where you are and how fast you're moving. This realization can be both mind-boggling and fascinating. So we see that time can stretch and squeeze, but can it disappear entirely? Imagine a place in space so dense, so massive, that it warps the fabric of space and time itself. Yes, we're talking about black holes. Black holes, these celestial monstrosities, are formed from the remnants of massive stars that have undergone a spectacular explosion known as a supernova. What's left collapses under its own gravity, creating a singularity, a point in space where density becomes infinite. Around this singularity, an event horizon forms, marking the point of no return. Now let's talk about gravity. It's not just an invisible force that keeps us grounded. It also has a profound influence on time. You see, according to Einstein's theory of relativity, the stronger the gravity, the slower time passes. This phenomenon, known as time dilation, has been observed and tested in numerous experiments. So what does this have to do with black holes? Well, a black hole's gravity is extraordinarily strong, so strong in fact, that it warps space and time to a spectacular degree. As you approach a black hole, the gravitational pull becomes increasingly powerful. Consequently, time begins to slow down relative to an observer far away from the black hole. As one reaches the event horizon, the outer boundary of the black hole, things get even stranger. Here the pull of gravity is so immense that time dilation reaches its extreme. For an observer watching from a safe distance, it would appear as though time has stopped for the unfortunate traveler at the event horizon. However, for the traveler themselves, time would appear to pass normally. This is one of the mind-bending realities of black holes. The concept of time becomes relative and warped. It's important to note, though, that this is all theoretical. Black holes are incredibly difficult to study due to their nature of absorbing all light and radiation. But with advancements in technology and our understanding of the universe, we may one day unlock more of their secrets. In the depths of a black hole, time as we know it ceases to exist. But what about areas devoid of matter and gravity? In the vast expanse of space, far from any star or planet, would time still tick away? Now, let's venture into the vast empty stretches of the universe, the cosmic voids. These are regions of space with a density much lower than the universe's average, almost devoid of galaxies, stars and planets. It's in these seemingly desolate expanses we ask the question, does time exist here? At first glance, you might think that time as we understand it would cease to exist. After all, there's no matter to interact with, no gravity to warp space-time, no celestial bodies to orbit, and no light to measure its speed against. But is that really the case? The answer lies in the cosmic microwave background radiation, or CMBR. This radiation is a relic from the Big Bang, the birth of our universe. It permeates all of space, filling even the emptiest voids. This omnipresent radiation provides a universal clock, a cosmic rhythm that persists even in the deepest, most desolate stretches of the universe. Let's take a moment to appreciate this. Even in the vast, empty voids of space, the CMBR's gentle hum provides a cosmic metronome, a universal beat. It's a reminder that time, as we understand it, is not solely dependent on matter, gravity, or light. It's a fundamental part of the fabric of the universe, woven into the very essence of existence itself. So even in the emptiness of these cosmic voids, time doesn't cease. It continues, unaffected by the lack of matter or gravity. It's not ticking away in the sense we're used to on Earth, measured by the rising and setting of the sun or the ticking of a clock. Instead, it's a constant, a silent and invisible companion to the cosmos. Even in the emptiness of space, time persists, a silent and invisible companion to the cosmos. Our journey through time and space has been nothing short of mind-bending. As we have explored, our perception of time is not as straightforward as we might think. It's not just about the ticking of a clock or the turning of a page on a calendar. It's an intricate part of the fabric of our universe, woven into the very essence of reality itself. We've delved into the concept of relativity, a revolutionary theory that has reshaped our understanding of time. Introduced by Albert Einstein, it revealed that time is not a fixed entity, but rather a variable, affected by speed and gravity. A minute on a speeding train is not the same as a minute sitting still. The faster you move, the slower time appears to pass. We journeyed to the depths of black holes, those mysterious cosmic entities where even light cannot escape. Here, the gravitational pull is so strong, time itself seems to stop. An hour inside a black hole could be an eternity outside of it. Yet despite their enigmatic nature, black holes are not the ultimate voids of timelessness. We ventured further, into the vast voids of space, seemingly empty and timeless. Yet even in these vast expanses, time persists. It's slower than on Earth, yes, but it doesn't cease to exist. It's a testament to the pervasiveness of time, a constant, unending stream that flows throughout the cosmos. But remember, our understanding of time is evolving. As we continue to explore the universe and develop new theories, our perception of time may change. It's a mystery that continues to baffle the brightest minds, a puzzle that we're still piecing together. As we've seen, time is more than just the ticking of a clock. It's a fundamental yet elusive part of our universe.